Picture this moment. Right now, as you watch this video, photons are streaming into your eyes that began their journey years ago. The light hitting your retina at this exact second left distant stars when you were a completely different person, living a completely different life. Some of these photons began traveling before you were born, before your parents were born, before human civilization existed. And the truly mind-bending part? This is normal. This is how the universe works every single second of every single day. Think about that for just a moment longer. Every time you look up at the night sky, you're not seeing the universe as it is right now. You're seeing a cosmic history book, with each star representing a different page, a different era. That bright point of light might be showing you what happened 50 years ago, or 500 years ago, or 5,000 years ago. The universe you see is a patchwork of different times, all arriving at your eyes simultaneously, all woven together into what appears to be a single moment, but is actually a tapestry of ancient light. And here is something even stranger. If you could somehow freeze time everywhere in the universe except Earth, and then travel instantaneously to those distant stars, you would find them completely different from how they appear to you tonight. Some might have exploded, some might have evolved into different types of stars, some might have developed planetary systems we cannot yet see. The universe you observe is not the universe that exists, it is the universe that existed at various points in the past, depending on how far away you are looking. We are quite literally looking back in time with every glance at the night sky. And the tool we use to measure these brain-melting distances, something called a lightyear. It sounds like a unit of time, which is part of what makes it so confusing, but it is absolutely, definitively, fundamentally a measurement of distance. Not time, distance. And it represents a span so incomprehensibly vast that even trying to wrap your mind around it might feel like attempting to hold the ocean in a teacup. The confusion is understandable. We live in a world where distance and time feel separate. When you drive to work, you think about the distance in miles or kilometers, and separately you think about the time it will take. 5 miles and 10 minutes, 20 kilometers and 30 minutes. Distance and time are related but distinct concepts in our everyday experience. But in the cosmos, at the scales we're about to explore, distance and time become so intertwined that they are essentially the same thing. Every unit of distance is also a unit of time delay. Every mile into space is a moment into the past. This is not metaphorical. This is not poetic language. This is literal truth about how the universe works. The reason it seems strange to us is because we evolved in an environment where the speed of light is effectively instantaneous. Light crosses a room in nanoseconds. It circles the Earth in a fraction of a second. For all practical purposes in human life, seeing something means seeing it now. But zoom out to cosmic scales, and that assumption breaks down completely. Seeing becomes time travel, distance becomes history, and nothing is ever now except right here where you're standing. Stop for a moment and really think about what happens when you look at the stars tonight. You're not seeing them as they are. You're seeing them as they were. That bright point of light you are looking at, it might not even exist anymore. It might have exploded in a supernova decades or centuries ago, and you would have no idea because the light from that explosion is still on its way, racing through the void at the fastest speed possible, not yet reaching Earth. You could be looking at ghosts, at echoes of stars that died before your grandmother was born. And it gets stranger. Every person who has ever looked at the night sky has seen a different universe than you see. Not because the stars moved, though they do, very slowly, but because they were looking at different moments in those stars' histories. Your great-great-grandfather looking at a star 100 light years away in the year 1900 saw that star as it was in the year 1800. You looking at the same star today see it as it was in 1925. Your great-great-grandchildren will see it as it will be in 2125. Same star, different moments in time, all visible from Earth but separated by the slow, steady passage of light through the cosmic void. This is not science fiction. This is not metaphor. This is the literal, physical reality of how the universe works. Distance equals time when you're talking about light. 1 light year away means 1 year in the past. 10 light years means a decade ago. 1,000,000 light years means 1,000,000 years into history. The universe does not have a universal now. Every point in space is experiencing a different now, and the only now you can ever truly know is your own, right here, right where you are. This is the story of the light year, of how humans created a way to measure the immeasurable, of why our evolutionary history left our brains spectacularly unequipped to grasp cosmic scales, of the strange, beautiful, frustrating reality that we're surrounded by distances so enormous that we cannot truly comprehend them, no matter how hard we try. We will journey from the moon to the edge of everything we can possibly see, and along the way, your understanding of space, time, and reality itself will never be quite the same again. Let me give you one number that sets the stage for everything else. If you wanted to walk to the nearest star beyond our sun, moving at a comfortable 3 miles per hour, never stopping to sleep or eat, maintaining that pace for every second of every day, it would take you 950 million years to arrive. That is longer than complex life has existed on Earth. That is more than twice the time since the dinosaurs went extinct, and that is the closest star. The universe beyond that? Well, strap in because things are about to get weird. Consider what 950 million years means. When you started your walk, the Earth was a very different place. The continents were arranged differently. The climate was alien. The dominant life forms were simple organisms without brains or eyes or bones. The walk from here to the nearest star would span almost the entire history of complex life on Earth. You would walk through the Cambrian explosion, when most major animal groups first appeared. You would walk through the rise and fall of the trilobites. You would walk through the evolution of fish, then amphibians, then reptiles, then dinosaurs. You would walk through the age of dinosaurs, all 180 million years of it. You would walk through their extinction and the rise of mammals. You would walk through the evolution of primates, then hominids, then humans. You would walk through all of recorded history. And then, finally, you would arrive at Proxima Centauri, having walked through almost 1 billion years of planetary evolution. And that is just to the nearest star. There are hundreds of billions of stars in our galaxy alone. There are hundreds of billions of galaxies in the observable universe, each separated by distances that make the gap to Proxima Centauri look like a stroll across the street. We are about to explore these distances, these light years, and try to make some sense of them. But I will tell you now, we will fail. You cannot truly comprehend these scales, neither can I, neither can anyone, but we can try, and in the trying we might just glimpse something beautiful about the universe and our place in it. Let us start with the fundamental question, because the name itself is one of astronomy's great sources of confusion. A light year sounds like it should be a measurement of time. After all, it has the word year right there in its name. Students in classrooms around the world regularly get this wrong, and honestly, who can blame them? But here is the truth that unlocks everything else. A light year is the distance that light travels in 1 year. Not how long it takes, the distance it covers. Light moves fast, stupendously, mind-bogglingly, impossibly fast by any standard we are used to. In 1 second, light travels 299,792 kilometers. That is 186,282 miles in a single second. To put that in perspective, light could circle the Earth more than 7 times in 1 second. In the time it takes you to snap your fingers, light has travelled far enough to wrap around our planet multiple times and still have distance to spare. Think about that for a moment. A commercial jet travels at about 900 kilometers per hour. That feels fast when you're on the plane, watching the ground blur beneath you. But light travels 300,000 kilometers per second, not per hour, per second. Light travels more distance in 1 second than a jet travels in almost 10 hours. If a jet and a photon were racing from New York to Los Angeles, the jet would take about 5 hours. The photon would arrive in about 16 thousandths of a second. The jet would still be taxiing on the runway when the photon reached the Pacific Ocean. And yet, despite this incredible speed, a second is not a year. So let us scale this up. In 1 year, specifically 1 Julian year of 365.25 days, light travels approximately 9.46 trillion kilometers. That is 5.88 trillion miles. The precise number, as defined by the International Astronomical Union, is 9,460,730,472,580.8 kilometers. But let's be honest, at this scale, the decimal places hardly matter when our brains can barely grasp trillion in the first place. To give you some sense of what a trillion even means, consider this. If you counted to 1 trillion, counting one number per second, never stopping to sleep or eat, it would take you about 32,000 years. That is longer than recorded human history. That is 4 times longer than civilization has existed. You would need to have started counting before the last ice age ended to finish now. And we are talking about 9.5 trillion kilometers. Not just 1 trillion or something, but 9.5 trillion. The human mind simply was not designed to work with these quantities. This staggering distance becomes our cosmic measuring stick. It emerged from necessity. Early astronomers quickly realized that using kilometers or miles for interstellar distances was absurd. Imagine writing out the distance to even the nearest star, 40,208,000,000,000 kilometers. The zeros become meaningless. The numbers stop conveying information and start just looking like abstract symbols on a page. We needed something bigger, something that matched the scale of what we were trying to measure. The concept traces back to 1838 when German astronomer Friedrich Bessel made the first successful measurement of the distance to a star beyond our solar system. He calculated the distance to 61 Cygni and noted that light would take about 10.3 years to traverse that gap. He did not use lightyear as an official unit, perhaps because the speed of light was not yet measured with sufficient precision, or perhaps because he recognized how strange it would sound. But the seed was planted. Bessel's achievement was remarkable in its own right. For centuries, astronomers had tried to measure the distances to stars and failed. The problem is that stars are so far away that they show almost no parallax, no apparent shift in position when viewed from different points in Earth's orbit. The angles involved are incredibly tiny, measured in fractions of an arcsecond. An arcsecond is 1/3600th of a degree. The parallax of even the nearest stars is less than 1 arcsecond. It is like trying to measure the width of a human hair from a kilometre away. Bessel succeeded by building a highly precise instrument called a heliometer, and by making meticulous observations over many months. He measured the tiny shift in position of 61 Cygni as Earth orbited the Sun, used trigonometry to calculate the distance, and arrived at a figure that, when converted to modern units, was remarkably accurate. He had proven that the stars were vastly farther away than anyone had imagined. The universe was much bigger than the solar system, much bigger than human intuition could grasp. When Bessel mentioned that light would take 10 years to travel that distance, he was making an observation, not proposing a unit. But the idea resonated. If light took 10 years to reach us from 61 Cygni, that gave people a way to think about the distance. It connected the abstract number of kilometers to something more tangible, the passage of time and the speed of the fastest thing anyone knew about. By the mid-1800s, the term began appearing in German astronomical texts. Otto Uhle, writing for a popular astronomy publication in 1851, explained this odd unit by comparing it to a walking hour, a common German measure of distance based on how far one could walk in an hour. The concept made intuitive sense. If you know how fast something moves and how long it moves for, you know the distance covered. A light year is simply that principle applied to the fastest thing in the universe moving for the longest common time period we regularly use. But the term took a while to catch on. For decades, different publications used different terminology. Some called it light travel distance. Others used light distance. The German term Lichtjahr appeared in various forms. English publications borrowed the concept but struggled with how to express it. By the late 19th century, light year had emerged as the standard English term, though some purists objected to its use. Not everyone was thrilled with this new unit. Some professional astronomers, including the famous Arthur Eddington, dismissed the light year as inconvenient and irrelevant, something that had crept from popular use into technical investigations. Professional astronomers preferred, and still prefer, another unit called the parsec, which is based on the geometry of how we measure stellar distances. 1 parsec equals about 3.26 light years. It is more directly tied to the measurement technique, but it is also completely opaque to anyone who is not an astronomer. The parsec, short for parallax second, is defined as the distance at which one astronomical unit, the Earth-Sun distance, subtends an angle of 1 arcsecond. If a star shows a parallax of 1 arcsecond, it is exactly 1 parsec away. If it shows a parallax of half an arcsecond, it is 2 parsecs away. The math works out cleanly for astronomers calculating distances from parallax measurements, but for everyone else, The parsec is just another abstract unit, no more intuitive than the lightyear. The lightyear persisted despite these objections because it does something the parsec cannot. It connects distance to something we understand intuitively, the passage of time and the speed of the fastest thing that exists. When someone says a star is 10 light years away, you immediately understand something profound. The light you see from that star is 10 years old. You're looking 10 years into the past. That connection between distance and time, that automatic understanding that greater distances mean older light, makes the light year conceptually powerful even if the actual distances involved remain incomprehensible. The speed of light itself has an interesting history. Ancient philosophers thought light travelled instantaneously, that the moment a torch was lit, its light appeared everywhere simultaneously. Galileo tried to measure the speed of light in the early 1600s using lanterns on distant hilltops, but the distances were too short and the speed too fast for his crude timing methods. He could only conclude that light was very fast, faster than he could measure. The first real measurement came from old Roma in 1676. He was studying the moons of Jupiter, timing when they disappeared behind the planet. He noticed that these eclipses happened earlier when Earth was moving toward Jupiter, and later when Earth was moving away. He realized this was because the light had to travel different distances depending on Earth's position in its orbit. By measuring these timing differences and knowing the size of Earth's orbit, he calculated that light must travel at a finite speed, about 225,000 kilometers per second by his estimate. This was remarkably close to the true value, especially given the limitations of 17th century astronomy. Over the next few centuries, measurements became more precise. In the 1800s, scientists measured the speed of light in laboratories using rotating mirrors and toothed wheels. By the early 20th century, the speed of light was known to high precision, and in 1983, the speed of light was officially defined as exactly 299,792,458 meters per second. This definition actually reversed the relationship between distance and time. Rather than measuring how fast light travelled, scientists decided to define the speed of light as a constant and use it to define what a meter is. The meter became the distance light travels in exactly 1,299,792,458th of a second. This might seem like a strange way to define a unit of distance, but it makes sense. The speed of light is a fundamental constant of nature. It does not change. It is the same everywhere in the universe, at all times. By tying our distance measurements to the speed of light, we ensure that our meter means the same thing everywhere and always. A meter on Earth is the same as a meter on Mars or in another galaxy or in the distant past or future, and make no mistake, these distances are incomprehensible. Not as a figure of speech, but as a literal description of how human brains function. We cannot actually grasp what 9 trillion kilometers means in any real, felt, visceral way. We can write it, we can calculate with it, we can compare it to other large numbers, but comprehend it? Feel it in our bones the way we feel the distance across a room, or even across a city? No, evolution did not prepare us for this. Our ancestors needed to estimate distances to predators and food sources, not to stars. The mental machinery simply is not there, but that is okay. Because even though we cannot truly comprehend these distances, we can still work with them, learn from them, and use them to map the universe. The light year gives us a tool to measure infinity, or at least the vast portions of infinity we can see. It lets us say one star is twice as far as another without drowning in meaningless zeros. It provides a conceptual framework that, while impossible to fully grasp, is at least consistent and useful. So when you hear light year from now on, remember, it is distance, not time. It is the ultimate road trip measured by the ultimate speed limit. It is how far light travels in a year, which happens to be far enough to make your brain hurt if you think about it too hard. And that is exactly as it should be. Because the universe is under no obligation to make sense to apes who only recently figured out fire. To understand the truly vast, we need to start with the merely enormous. Let us build our way up the cosmic distance ladder, rung by rung, until we reach scales that defy all intuition. We begin at the bottom, with the closest thing to Earth in the entire universe, our moon. The moon sits, on average, about 384,000 kilometers from Earth. In light terms, that distance is covered in approximately 1.3 seconds. This is a light second, not a light year, but it is a crucial starting point. That 1 second delay is why astronauts on the moon experienced a noticeable pause in their communications with mission control. Ask a question, wait a second for the signal to reach the moon, wait another second for the response to return. 2 seconds of awkward radio silence built into every exchange, a small reminder that even our closest neighbour is really quite far away. But let us put that 384,000 kilometres in more familiar terms. That is roughly the distance you would travel if you drove around the Earth's equator 9.5 times. Imagine getting in your car and circling the globe, then doing it again and again and again 9.5 times in total. That is how far away the moon is. If you could drive to the moon at highway speed 60 miles per hour, never stopping for gas or sleep or anything else, it would take you about 6 months to get there. The Apollo astronauts, travelling faster than any humans before them, needed 3 days. And consider what those 3 days meant. The astronauts were sealed in a capsule the size of a small car, hurtling through space at over 35,000 kilometers per hour. That is nearly 10 kilometers every second. That is faster than a bullet, faster than anything humans had ever travelled in before. And even at that blistering pace, it took 3 days to cover the distance. They launched from Earth, watched their home planet shrink to the size of a marble, then to a star, floating in the blackness. They coasted through empty space, no longer on Earth, but not yet on the moon, suspended between worlds. And finally, after 3 days, they arrived. The moon is close, by cosmic standards, but it is still far enough that we cannot simply visit it on a whim. We need massive rockets, months of planning, enormous expense. The distance is manageable but not trivial. It represents the outer edge of what feels achievable with current human technology. Beyond the moon, distances start to become harder to work with. Now let us step farther out to the cosmic object that makes all life on Earth possible, the Sun. The Sun sits approximately 150 million kilometers from Earth, a distance we call an astronomical unit, or AU. This is our first real cosmic measuring stick. In light terms, the Sun is about 8.3 light minutes away. Not light years, but light minutes. The light that is warming your face right now, if you're outside on a sunny day, left the Sun 8 minutes ago. You're not seeing the Sun as it is now. You're seeing the Sun as it was 8 minutes ago. This has real consequences. If the Sun suddenly vanished, we would not know for 8 minutes. We would continue to see it, continue to feel its warmth, completely unaware that it was already gone. For 8 glorious, ignorant minutes, everything would seem normal. Then darkness would fall. That is not a scenario you need to worry about, by the way. The Sun is not going anywhere for about 5 billion years, but it illustrates an important principle. When you look at anything in space, you're always looking at the past. Always. There is no now in astronomy, only then. Think about what 8 light minutes means in practical terms. Every sunrise you have ever seen actually happened 8 minutes before you saw it. Every sunset occurred 8 minutes before the sky turned orange and gold. When you look at the Sun, you're looking at its surface as it was 8 minutes earlier. If a massive solar flare erupted right now, you would not see it for 8 minutes. If the Sun's light suddenly changed colour, you would not notice for 8 minutes. There is an 8-minute gap between reality on the Sun and reality on Earth, a gap imposed by the finite speed of light. If you wanted to drive to the Sun, maintaining that same highway speed of 60 miles per hour, it would take about 170 years. You would need multiple generations of drivers, passing the wheel from great-grandparent to great-grandchild before anyone in your family saw their destination. And remember, this is our closest star, the one we orbit, the one that dominates our sky, the one that makes life possible. It is so close that we can feel its warmth and see it with the naked eye. And yet it is 170 years of driving away. Let us zoom out a bit more, to the edge of our solar system. Neptune, the outermost major planet, orbits at about 30 astronomical units from the Sun, roughly 4.5 billion kilometers. Light from the Sun takes about 4 hours to reach Neptune. That means if you were standing on Neptune watching a sunrise, you would be seeing the Sun as it was 4 hours earlier. The sunset would show you the Sun from 4 hours before that. This 4-hour light travel time has practical implications for space exploration. When NASA's Voyager 2 spacecraft flew past Neptune in 1989, every command sent from Earth took 4 hours to reach the spacecraft. Every picture taken by Voyager took 4 hours to arrive back at Earth. If something went wrong, if the spacecraft needed to make an emergency correction, there would be no time for human intervention. The spacecraft would either fix itself using its onboard computers, or it would fail. The humans controlling it from Earth were simply too far away to help in real time. Pluto, sometimes considered the edge of the classical solar system, sits at roughly 40 astronomical units, about 6 billion kilometers out. Light takes 5.5 hours to make that journey. When the New Horizons spacecraft flew past Pluto in 2015, it was operating autonomously, following pre-programmed instructions, because the 5.5-hour signal delay made real-time control impossible. The humans on Earth watched what New Horizons had done 5.5 hours earlier, hoping everything had gone according to plan. But the solar system does not really end at Pluto. Far beyond, in the cold darkness, sits the Oort cloud, a spherical shell of icy bodies that marks the true edge of the Sun's gravitational influence. The inner edge of the Oort cloud is estimated to be around 2,000 AU from the Sun. The outer edge, perhaps 100,000 AU. At the outer reaches of the Oort cloud, about 1.5 to 2 light-years from the Sun, we finally cross a threshold. We are now measuring interstellar distances, the gaps between stars, in actual light-years rather than light-minutes or light-hours. And this is still within the Sun's domain, the region of space where the Sun's gravity is the dominant force. We have not even left home yet, and we are already dealing with light-years. To reach this outer edge of the Oort cloud at light speed would take nearly 2 years. At the speed of the Voyager 1 spacecraft, humanity's fastest and farthest travelling object, moving at about 17 kilometers per second, it would take nearly 40,000 years. And Voyager 1 is hauling along at 11 miles per second, a speed so fast it seems absurd by terrestrial standards. Yet measured against cosmic distances, it crawls like an ant. Think about Voyager 1 for a moment. It launched in 1977, nearly half a century ago. It has been travelling without pause ever since, moving away from the Sun at 11 miles per second. It will continue travelling for thousands of years, long after everyone who built it has died, long after the space agencies that launched it have been forgotten, and in 40,000 years it will finally maybe reach the outer edge of the solar system. Not another star, just the edge of our own solar system. This is where our intuition begins to fail us completely. We can sort of imagine driving for 170 years to the Sun, even though it is absurd. We can conceptualize the Moon as 9 trips around Earth. But 40,000 years to reach the edge of the solar system? That is longer than recorded human history. That is longer than agriculture has existed. And we are still in our cosmic backyard, still within the gravitational embrace of our own star. Yet even these distances are nothing, absolutely nothing compared to the gulfs between stars. The Oort cloud represents the last outpost of our solar system. Beyond it lies something that most people do not fully appreciate: emptiness. Vast, profound, almost incomprehensible emptiness. The space between stars is not just distance, it is a kind of void that defies description. A nothingness so complete that it makes the space between Earth and the Moon look crowded by comparison. We measure these smaller distances to build intuition, to give ourselves reference points. The Moon is a light second away, the Sun is 8 light minutes, Neptune is 4 light hours. The Oort cloud is a light year or 2. Each step prepares us for the next, builds the ladder one rung at a time, but understand this. No amount of preparation truly readies the human mind for the distances we're about to encounter. We're about to step off the ladder into the true depths of space, and everything that seemed impossibly far will suddenly seem like the house next door. Take everything we have discussed so far about distance, every measurement, every comparison, every attempt to make sense of the space between Earth and the far reaches of our solar system. Now multiply it by 1,000, then multiply it again. That gives you a rough sense of the distance to the next star over. The nearest star to our Sun is Proxima Centauri, a small, dim red dwarf in the constellation of Centaurus. It sits 4.24 light-years away, or about 40,208 billion kilometers. If you prefer miles, that is about 25 trillion miles. These numbers have lost all meaning, have not they? Your brain just sees trillion and shrugs. Let me try to make this slightly less abstract, even though it will still be impossible to truly grasp. Remember how it would take 40,000 years for Voyager 1 to reach the outer edge of our solar system? To reach Proxima Centauri, Voyager 1 would need 73,000 years, and that is only if it were pointed in the right direction, which it is not. That is 365,000 human generations. That is longer than modern humans have existed as a species. If our ancient ancestors from 73,000 years ago had launched Voyager 1 toward Proxima Centauri, it would be arriving right about now, and those ancestors were Neanderthals who had not yet developed agriculture, writing, or civilization. If you could somehow travel at the speed of light, which physics tells us is impossible for anything with mass, you would still need 4.25 years to reach Proxima Centauri. 4 years of travelling at the fastest speed possible in the universe, crossing nearly 10 trillion kilometres every year. And you would just barely reach the nearest star. The fastest thing that exists, moving without stop, would need over 4 years to make the trip. Walking there, at a comfortable 3 miles per hour, you would need 950 million years. That is longer than multicellular life has existed on Earth. Dinosaurs evolved and went extinct twice over in less time than it would take you to walk to Proxima Centauri. Every step you took would cover 3 miles, and you would need to take 248 trillion of those steps, without stopping, ever. Proxima Centauri is part of a triple star system called Alpha Centauri. The other 2 stars in the system, Alpha Centauri A and B, are slightly farther away, about 4.37 light-years distant. These 2 stars orbit each other in a dance that takes about 80 years to complete. Proxima Centauri orbits this pair at a much greater distance, taking about 550,000 years for a single orbit. The 3 stars are gravitationally bound, a family of stars in the vastness. And here is where things get interesting in a different way. Proxima Centauri has planets, at least 3 that we know of. Proxima Centauri b, discovered in 2016, is about 1.3 times Earth's mass, and orbits in what astronomers call the habitable zone, the region where liquid water could exist on a planet's surface. It completes an orbit in just 11.2 Earth days because it orbits very close to its star, about 7.5 million kilometers out, much closer than Mercury is to our Sun. The light we see from Proxima Centauri right now left that star 4.25 years ago. Think about that for a moment. If you look at Proxima Centauri through a telescope tonight, you're seeing it as it was in 2021. You're seeing photons that began their journey across the interstellar void when we were still deep in the pandemic, when the world was a different place. Any changes that have happened at Proxima Centauri in the last 4 years are invisible to us. They have not arrived yet. They're still on their way, travelling through the emptiness at the speed of light. If some catastrophe destroyed Proxima Centauri tomorrow, we would not know until 2029. We would look at it in our telescopes, seeing it shine, completely unaware that we were looking at a ghost, at light from a star that no longer exists. And if intelligent life exists on Proxima Centauri b, and if they are looking at Earth right now, they are seeing Earth as it was 4.25 years ago. They are seeing us in 2021. Any message we send to them would take 4.25 years to arrive. Any reply would take another 4.25 years to return. A simple hello and its response would span more than 8 years. This is not a large distance by cosmic standards. Proxima Centauri is our next-door neighbour. It is in our cosmic neighbourhood, part of our immediate stellar vicinity, and yet it might as well be infinitely far away for all the possibility we have of reaching it with current technology. The fastest spacecraft humanity has ever built, the Parker Solar Probe, can reach speeds of about 430,000 miles per hour when it dives close to the Sun. Even at that blistering pace, it would take about 6,000 years to reach Proxima Centauri. Other nearby stars paint the same picture of vast distance. Barnard's star sits about 6 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years distant. The reason Sirius is so bright is not because it is especially close, but because it is an intrinsically luminous star. Proxima Centauri, despite being closer, is invisible to the naked eye because it is a dim red dwarf, emitting only about 0.17% of the Sun's light. You need a telescope to see our nearest neighbour. Within 10 light-years of the Sun, there are only about a dozen star systems. In 20 light-years, that number grows to about 100. These are our neighbours in the most generous possible definition of the word. These are the stars we would visit first if we ever developed the capability for interstellar travel, and every single one of them is impossibly far away. The average distance between stars in our region of the galaxy is about 5 light-years. That is typical. Stars are not crowded together. They are separated by almost inconceivable gulfs of emptiness. If you built a scale model of our local stellar neighborhood, where the Sun was the size of a grain of sand, Proxima Centauri would be another grain of sand about 300 meters away. And between them, nothing. Empty space. A void. This is what space is mostly made of. Not stars, not planets, not gas or dust or anything else, just void. Empty, dark, cold void. The distances between things are so much larger than the things themselves that the universe is, in a very real sense, mostly nothing. Matter is the rare exception. Emptiness is the rule. And yet, despite these crushing distances, despite the fact that our nearest neighbour is so far away it might as well be in another dimension, we can still see it. The light reaches us. Information spans the gap. We can study Proxima Centauri, measure its properties, discover its planets, understand its nature, all from 4.25 light years away. Distance does not equal ignorance in astronomy. It equals time delay, but not necessarily mystery. That is the strange gift of the light year as a measurement. It is both a distance and a time machine. Every light year we look is another year into the past. 1 light year away shows us 1 year ago. 10 light years shows us a decade past. The farther we look, the older the light, the deeper into history we peer, and as we are about to see, some of the things we observe are not just years old, but millions and billions of years old. Light that began its journey when the universe itself was young and Earth did not yet exist. Let us pause here and address something fundamental. Why does all of this feel so impossible to grasp? Why can you read that Proxima Centauri is 40 trillion kilometers away, and your brain just sort of refuses to process what that means? It is not because you're bad at astronomy or math. It is because your brain, like every human brain, evolved to do something completely different. Your ancestors did not need to estimate distances to stars. They needed to estimate distances to predators. They needed to judge whether they could outrun a lion or whether that rustle in the grass was a snake. They needed to throw rocks accurately at rabbits and know how far to walk to find the next water source. The selection pressures that shaped human cognition had nothing to do with cosmic scales, and everything to do with survival in an environment measured in meters and kilometers, not light years. As a result, we have an intuitive sense of scale that breaks down somewhere around a few kilometers. You can walk a kilometer and feel it. You can see a few kilometers on a clear day. You can imagine 10 kilometers because you have probably driven that distance. Maybe you can stretch to 100 kilometers if you have taken a long road trip. But 1,000 kilometers? 10,000? The numbers start losing meaning. Your brain has no experiential reference for them. This problem compounds exponentially as numbers grow. There is a classic example that illustrates this perfectly: the difference between 1 million and 1 billion. If you count to 1 million, counting one number per second, it would take you about 11.5 days. If you count to 1 billion at the same pace, it would take you 31.5 years. Million and billion sound similar. They are both big round numbers, but one is 2,700 times larger than the other, a gap our brains struggle to appreciate viscerally. Now apply that to astronomical distances. The distance from Earth to the Moon is about 400,000 kilometers. The distance from Earth to the Sun is about 150 million kilometers. The distance to Proxima Centauri is about 40 trillion kilometers. Each step multiplies the distance by roughly 1,000 or more, and we have only just started. The distances to nearby galaxies are measured in millions of light years, which means trillions of kilometers. The observable universe extends for tens of billions of light years. Psychologists call this problem scope insensitivity or psychic numbing. Our emotional and intuitive response to large numbers is remarkably flat. Whether you tell someone that 1,000 birds died in an oil spill or 1 million birds died, their emotional reaction is surprisingly similar. The numbers are both big, and that is where our brains stop making distinctions. The same thing happens with astronomical distances. Whether something is 1,000 light years away or 1 million light years away, both are simply very far, and our brains do not meaningfully distinguish between them at an intuitive level. This is not a flaw in reasoning. It is a feature of how cognition works. Our brains use analogies and metaphors to understand new information. We map unfamiliar concepts onto familiar ones. When I told you it would take 950 million years to walk to Proxima Centauri, that might have landed with more impact than 40 trillion kilometers, because you have experience with walking and with years, even if you do not have experience with 950 million of them. The metaphor provides a scaffold for understanding, even if true comprehension remains out of reach. Scientists and educators have developed countless analogies to help people grasp astronomical scales. If the Earth were a peppercorn, the Sun would be a beach ball 200 meters away. If the Sun was scaled down to the size of a grain of sand, Proxima Centauri would be another grain of sand 300 meters away. If the Milky Way were the size of the United States, our solar system would be about the size of a quarter. These comparisons help, but they also reveal how inadequate our tools are. We are trying to make the incomprehensible comprehensible, and the best we can do is make it slightly less incomprehensible. There is also a temporal component to this cognitive challenge. We struggle not just with large distances, but with large timescales. A light year is both a distance and a journey through time. When we look at something 1 light year away, we see it as it was 1 year ago. This conflation of space and time is deeply embedded in how the universe works, but it is not how our everyday experience works. In our daily lives, now is now everywhere. When you video chat with someone on the other side of the world, there is maybe a fraction of a second of delay. For all practical purposes, you are experiencing the same now. But look at a star 100 light years away, and now loses all meaning. What is happening at that star right now, at this moment? You cannot know. You cannot see it. The information has not arrived yet. You can only see what was happening there 100 years ago. If aliens on a planet orbiting that star were looking at Earth right now with a powerful telescope, they would see Earth in the year 1925. They would see a world without internet, without nuclear weapons, without jet aircraft. They would see a completely different version of human civilization. This is not metaphorical. This is literal. Distance and time are connected in a way that our brains, evolved to navigate local three-dimensional space, find almost impossible to internalize. Einstein showed us that space and time are not separate things but different aspects of a four-dimensional space-time. The farther away something is in space, the farther back in time you see it. This is fundamental to how reality works, not a quirk or an artifact, and it breaks our intuition completely. Some researchers have studied how people develop what they call cognitive stretch, the ability to work with concepts far outside normal human experience. Physicists and astronomers develop strategies for thinking about the very large and very small. They use mathematics as a language that allows precise reasoning even when intuition fails. They build mental models and frameworks that let them manipulate ideas they cannot truly picture. It is a kind of conceptual scaffolding, a way of thinking about things indirectly that would be impossible to think about directly. Consider how astronomers actually think about these distances. They do not sit at their desks trying to visualize what 40 trillion kilometers looks like. Instead, they work with ratios, with relationships between distances. Proxima Centauri is roughly 270,000 times farther from Earth than the Sun is. That ratio is manageable. You can understand that something is 270,000 times bigger than something else, even if you cannot visualize either quantity absolutely. This is how scientists navigate the incomprehensible, by relating it to other things, by building chains of comparisons. They also use logarithmic thinking, where distances are thought of in orders of magnitude rather than absolute values. The Moon is roughly 10 to the 8th power meters away. The Sun is 10 to the 11th power. Proxima Centauri is 10 to the 16th power. Each step is a multiplication by 1,000 or more, but thinking in powers of 10 makes the progression cleaner, more manageable. This is why scientists love logarithmic scales. They compress vast ranges into spaces our minds can work with, but even professional astronomers, people who work with these numbers every day, will tell you they do not really grasp them. They work with them. They calculate with them. They understand their relationships to other numbers. But viscerally feel what 1 billion light years means? No, that is beyond human capability. We are apes with fancy tools, able to measure and understand things intellectually that we will never be able to comprehend emotionally or intuitively. There is actually a name for the cognitive bias that makes large numbers feel similar to each other. It is called scope neglect, or scope insensitivity, and it affects how we respond emotionally to quantities. In experiments, people shown photographs of a starving child are willing to donate similar amounts of money whether they are told the money will save 1 child or save 10 children or save 100 children. the scope of the problem, the number of children makes surprisingly little difference to the emotional response. 1 is bad, 10 is bad, 100 is bad, and our brains stop making fine distinctions beyond that. The same principle applies to cosmic distances. 1 trillion kilometers is far, 10 trillion is far, 100 trillion is far. Our emotional and intuitive response flattens out. We cannot feel the difference between these quantities, even though one is 100 times larger than the other. This is not a failure of intelligence, it is a fundamental feature of how human cognition evolved. We needed to distinguish between 3 apples and 5 apples. We did not need to distinguish between 3 billion apples and 5 billion apples, because those quantities never appeared in our ancestral environment. Children display this limitation even more starkly than adults. Studies have shown that young children often think the moon is about as far away as another city or maybe another country. The idea that it is hundreds of thousands of kilometers away in the vacuum of space is simply beyond their conceptual framework. As we grow and learn, we can accept these distances intellectually, but the intuitive sense never fully catches up. Even adults who know the moon is far away do not have a visceral, felt sense of that distance the way they have a felt sense of the distance across their living room, and maybe that is okay. Maybe it is even beautiful in a strange way. We are limited creatures in an unlimited universe, and yet we've figured out how to map that universe anyway. We have created tools like the lightyear that let us span the gap between our limitations and the cosmos. We cannot feel these distances, but we can measure them, study them, learn from them. We are small, but we are not helpless. We are constrained, but we're not ignorant. Some philosophers and scientists have argued that this inability to comprehend cosmic scales is actually a form of existential humility. We are forced to confront the fact that the universe does not operate on human scales, that we are not the measure of all things, that reality extends far beyond what our senses and intuitions can grasp. This can be frightening or it can be liberating, depending on how you approach it. On one hand, it is humbling to realize that you cannot truly understand something as basic as how far away the stars are. It highlights our limits, our smallness, our insignificance in the grand scheme of things. On the other hand, it is empowering to realize that despite these limits, we have still managed to measure the stars, to map the universe, to understand how it works. We have transcended our biological limitations not by overcoming them, but by building tools and methods that work despite them. The history of science is, in many ways, a history of humans finding ways to extend beyond what our unaided senses and brains can perceive. We invented telescopes to see farther than our eyes allow. We invented mathematics to reason about quantities our intuition cannot grasp. We invented the scientific method to test ideas more rigorously than our biases would permit. And we invented units like the lightyear to measure distances that would otherwise be unmeasurable. Each of these inventions is an acknowledgement of our limits, and simultaneously a way of transcending them. We cannot see distant galaxies with our naked eyes, so we build telescopes. We cannot intuitively grasp trillions of kilometers, so we invent light years. We cannot hold the entire universe in our heads, but we can build models and equations that capture its essential features. The universe is vastly, incomprehensibly large. Your brain is not capable of truly grasping its scale. Both of these things are true. And somehow, despite that second truth, humanity has still managed to map the cosmos, to understand how stars form and die, to predict the fate of galaxies billions of years from now, to look back in time to the birth of the universe itself. We cannot comprehend the scale, but we have comprehended the physics, and that might be the most remarkable thing about our species. We are pattern recognition machines, evolved to find food and avoid predators, and we have somehow turned that basic cognitive toolkit into something powerful enough to measure infinity. We cannot feel a light year, but we can define it, calculate it, use it to map the structure of reality. We are small temporary creatures on a small temporary planet, and we have looked out into the void and understood what we saw. That is extraordinary. That is worth celebrating, even as we acknowledge how little we truly comprehend. If the distances between stars in our local neighborhood seem incomprehensible, then the scale of our galaxy should probably just cause your brain to quit entirely. But we press on, because the journey is not complete until we have truly appreciated the full scope of cosmic distances. So let us zoom out from our solar system, from our nearby stars, and look at the larger structure we call home, the Milky Way galaxy. The Milky Way is a spiral galaxy, shaped like a disk with a bright central bulge and sweeping spiral arms extending outward. From edge to edge, it measures approximately 100,000 light-years across. Let that sink in. 100,000 light-years. That means light, travelling at its unimaginable speed, would need 100,000 years to cross from one side of our galaxy to the other. If a photon left one edge of the Milky Way right now, it would arrive at the opposite edge in the year 100,2025, long after every current human civilization has crumbled to dust, assuming humans even still exist. Our solar system is not at the centre of this vast structure. We sit about 27,000 light-years from the galactic centre, roughly 2/3 of the way out from the middle to the edge. We are in one of the spiral arms, specifically the Orion arm or Orion spur, a minor spiral arm between two larger ones. We are cosmically speaking in the suburbs, not at the bustling city centre, not in the remote countryside, but in a moderately dense residential area of the galaxy. 27,000 light-years to the galactic centre means that when you look toward the centre of the Milky Way, you're seeing it as it was 27,000 years ago. The light hitting your eyes began its journey long before recorded history, before agriculture, before the last ice age ended. Human beings were still living in small hunter-gatherer bands when that light began its voyage. Everything we call civilization has happened while that light crossed the galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that estimate is itself 100 billion stars, more than the number of stars in many smaller galaxies. These stars are not evenly distributed. They cluster more densely near the centre and thin out toward the edges. In our region of the galaxy, the average distance between stars, as we discussed, is about 5 light-years. Near the centre, stars are packed much more tightly with typical separations of maybe 1 light-year or less. But even with 400 billion stars, even with all that matter, the galaxy is mostly empty space. The scale of the emptiness is hard to overstate. If you scale the Milky Way down so that the distance between the Sun and Proxima Centauri, 4.2 light-years, was just 1 inch, the galaxy would still be about 20,000 miles across. The entire Earth is only about 8,000 miles in diameter. The scaled-down galaxy would be 2.5 times wider than Earth, and the space between stars would be represented by 1-inch gaps. At the centre of our galaxy sits a supermassive black hole called Sagittarius A star with a mass about 4 million times that of the Sun. This black hole is surrounded by a dense cluster of stars, some of which orbit the black hole at speeds reaching several % of the speed of light. Astronomers have been tracking these stars for years, watching them complete orbits that take decades or centuries. The light from this region, remember, is 27,000 years old by the time we see it. We are watching ancient history play out in what we call real time. The Milky Way is not alone in space. It is part of a group of galaxies called the Local Group, which contains about 80 galaxies in total. Most of these are dwarf galaxies, small collections of stars gravitationally bound to the two giants of the group, the Milky Way and the Andromeda galaxy. These dwarf galaxies orbit the larger galaxies like moons orbit a planet held in place by gravity, dancing slowly through the cosmic void over timescales of hundreds of millions of years. The thickness of the Milky Way's disk is much smaller than its width, maybe a few thousand light-years depending on how you measure it. This creates a flattened, pancake-like structure. Our solar system moves through this disk, orbiting the galactic centre once every 225 to 250 million years. This is called a galactic year or a cosmic year. Earth has completed about 20 of these orbits since it formed 4.5 billion years ago. The last time our solar system was in its current position relative to the galaxy, dinosaurs had only recently appeared. The time before that, the earliest complex life was just beginning to emerge in Earth's oceans. We are moving through the galaxy at about 230 kilometers per second relative to the galactic center. That is about 514,000 miles per hour. You are, right now, hurtling through space at 500,000 miles per hour on a 250 million year journey around the galaxy. And you feel none of it because everything around you is moving with you. The Earth, the Sun, the nearby stars, all caught in the same orbital dance. Light from the far side of the galaxy 100,000 light-years away shows us that region as it was when anatomically modern humans were just beginning to appear in Africa. If someone over there is looking back at us with a telescope right now, they are seeing Earth 100,000 years ago, a world populated by early humans who had not yet spread across the planet, who had not yet developed language as we know it, who had not yet created art or writing or any of the things we think of as distinctly human. The galaxy itself is not static. It is rotating, with different parts rotating at different speeds, creating the spiral arm structure. These arms are not fixed structures, but density waves, regions where stars temporarily cluster as they orbit. Imagine a traffic jam on a highway. The cars that make up the jam are constantly changing as cars enter from behind and leave from the front. But the jam itself persists. Spiral arms work similarly, with stars and gas flowing through them. The Milky Way has consumed other, smaller galaxies in its past and will consume more in its future. The dwarf galaxies orbiting our galaxy are slowly being torn apart by tidal forces, their stars scattered and absorbed into the larger structure. In a few billion years, the Milky Way will collide with Andromeda, and the two will merge into a new, larger galaxy. But that is a story for a few sections ahead. For now, just try to picture this: 100,000 light years across, 400 billion stars, vast spiral arms of stars and gas and dust, rotating slowly around a supermassive black hole at the center. The whole structure moving through space, part of a larger group of galaxies, part of an even larger cosmic web of structures stretching across billions of light years. And somewhere in one of the spiral arms, about 2/3 of the way out from the center, a small yellow star with a family of planets, including one blue world where creatures made of stardust have evolved to look up at the night sky and wonder about all of this. That is our galaxy, our home on the largest scale we can really call home. Beyond this, beyond the Milky Way, we enter a realm of distances so large that even light years start to become unwieldy. We will need bigger units, bigger comparisons, bigger frameworks for thinking, because as vast as the galaxy is, it is just the beginning. The universe extends far, far beyond the Milky Way, and we are about to step out into that larger cosmos. On a dark, clear night far from city lights, if you know where to look in the constellation Andromeda, you can see something remarkable with your naked eye. It appears as a faint, fuzzy patch of light, easy to miss if you do not know it is there. It looks like nothing special, just a slightly brighter smudge against the dark sky. But that smudge is the Andromeda Galaxy, and it is about 2.5 million light years away. Let me say that again because it deserves to be said slowly. 2.5 million light years. The light reaching your eyes right now from Andromeda began its journey 2.5 million years ago. When that light started travelling, there were no humans on Earth. Not modern humans, not even our direct ancestors. The creatures that would eventually give rise to the human lineage were still evolving in Africa. Early stone tools had not yet been invented. The continents were in slightly different positions, the climate was different, and a photon left Andromeda, travelled through the vast emptiness between galaxies, crossed 2.5 million light years of space, and arrived tonight in your eye. Andromeda, also called Messier 31 or simply M31, is the closest large galaxy to the Milky Way. It is a spiral galaxy like ours, maybe slightly larger, containing perhaps 1 trillion stars compared to our few hundred billion. Its disk spans about 220,000 light-years across, roughly twice the diameter of the Milky Way. If you could see the full extent of Andromeda in the night sky, it would appear 6 times wider than the full moon, an enormous bright patch dominating that region of the heavens. But most of its light is too faint for our eyes to detect, so we see only the bright central core. For most of human history, Andromeda was called a nebula, assumed to be a cloud of glowing gas within our own Milky Way. The debate about its true nature was fierce. In 1920, astronomers Harlow Shapley and Heber Curtis held what became known as the Great Debate about the scale of the universe and whether spiral nebulae like Andromeda were part of our galaxy or separate island universes far beyond it. The question was settled in 1925 when Edwin Hubble, using the newly built Hooker telescope on Mount Wilson, identified Cepheid variable stars in Andromeda. These stars pulse with a regular rhythm, and their pulsation period is directly related to their intrinsic brightness. By comparing their apparent brightness in the sky to their intrinsic brightness, Hubble calculated their distance and proved that Andromeda was vastly further away than anything else in the Milky Way. It was indeed a separate galaxy, an island universe in its own right. This discovery fundamentally changed our understanding of the cosmos. The universe was not just the Milky Way, it was vastly larger, filled with countless other galaxies, each containing billions or trillions of stars. Andromeda was the first galaxy proven to exist beyond our own, the first island in an ocean we were only beginning to explore. And it was unimaginably far away. 2.5 million light-years is a distance that strains every metaphor. If you could travel at the speed of light, you would need 2.5 million years to get there. If you travelled at the speed of Voyager 1, the fastest spacecraft we've ever sent into deep space, you would need about 76 billion years, far longer than the current age of the universe. The entire history of the cosmos is not long enough for that journey. Andromeda is moving toward us. The light from it is blue-shifted, meaning its wavelengths are compressed, indicating motion in our direction. It approaches at about 110 kilometers per second. Despite this speed, the collision will not happen for about 4 billion years because the distances involved are so vast. Covering 2.5 million light-years, even at 110 kilometers per second, takes an almost incomprehensible amount of time. When Andromeda and the Milky Way collide, it will be one of the most dramatic events in the history of both galaxies. The stars themselves will likely not collide. The distances between them are too great, but the gravitational interactions will be profound. Stars will be flung out into intergalactic space. New waves of star formation will ignite as gas clouds collide and compress. The two supermassive black holes at the centers of the galaxies will eventually merge into an even larger black hole. The final result, billions of years after the collision begins, will be a single large elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda by astronomers with a sense of humour. But this is all in the distant future. For now, Andromeda sits across the void, 2.5 million light-years away, close enough to see with the naked eye but too far to reach with any technology we can imagine. It is our nearest large galactic neighbour, part of the local group, bound to us by gravity, on a slow collision course that will reshape both galaxies. Think about what it means to see something 2.5 million light-years away. Every photon carrying information from Andromeda to Earth has been travelling for 2.5 million years. These are not metaphorical years. They are actual years of travel through the vacuum of space. During that time, the photons have crossed an incomprehensible distance, passed through the space between galaxies, navigated the weak gravitational fields of dark matter, and finally arrived at Earth to be captured by your eye or a telescope. And here is something even stranger. The version of Andromeda we see is 2.5 million years out of date. If something dramatic happened there today, we would not know for 2.5 million years. If someone in Andromeda is looking back at us right now, they are seeing Earth as it was 2.5 million years ago in the Pleistocene epoch, with early hominids just beginning to use stone tools. They are not seeing modern humans because modern humans did not exist yet in the version of Earth visible to them. This is the nature of cosmic distances. They're also time machines. The farther away something is, the further back in time we see it. This is not an artifact or a quirk. It is fundamental to how information propagates through the universe. Light travels at a finite speed, and distance equals time. 1 light-year of distance equals 1 year of time lag. 2.5 million light-years equals 2.5 million years of lag. Andromeda contains about 1 trillion stars, more than twice as many as the Milky Way. It has its own retinue of satellite galaxies, smaller galaxies orbiting it. It has likely consumed other galaxies in its past, growing larger through collisions and mergers. It is a complex dynamic system, a vast collection of stars and gas and dark matter, all held together by gravity, rotating slowly, evolving over billions of years. And we can study it in detail despite the distance. We can measure the motions of stars within it. We can identify different regions of star formation. We can map its spiral arms and dust lanes. We can detect its supermassive black hole. Distance is no longer ignorance in modern astronomy. Distance is merely time delay. We cannot interact with Andromeda in real time, but we can observe it, learn from it, understand it. This is the power of light and of light years as a measure. Information spans the void. Even 2.5 million light years is not enough to keep secrets. The universe is transparent to light, and light carries knowledge across even the vastest gulfs. Every photon is a messenger, bringing news from distant places and distant times. And when we look at Andromeda, we are reading messages that were sent when Earth was a very different world, in a very different age. We have been climbing a ladder of distance, each rung vastly larger than the last, from the moon to the sun, from the sun to the nearest stars, from those stars to the span of our galaxy, from our galaxy to Andromeda, each step multiplying the distance by factors of thousands or millions. And now we reach the final rung, the ultimate scale, the largest distance humans can possibly measure or conceive, the observable universe. The observable universe is the spherical region of space from which light has had time to reach us since the Big Bang. Its radius is approximately 46.5 billion light-years in all directions. That makes its diameter about 93 billion light-years. And immediately you should notice something strange about these numbers. The universe is about 13.8 billion years old. Light has been travelling toward us for 13.8 billion years. So how can the observable universe be 93 billion light-years across? Should it not be only 27.6 billion light-years across, twice the age of the universe? This is where the expansion of space enters the picture. The universe is not static. Space itself is stretching, and it has been stretching throughout the history of the cosmos. When light left the most distant galaxies we can see, those galaxies were much closer to us than they are now. But while the light was travelling toward us, the space between us and those galaxies expanded, carrying them farther away. By the time the light arrives, the galaxy that emitted it is much more distant than it was when the light began its journey. Think of it like this. Imagine ants walking across the surface of a balloon while you inflate it. The ants are moving, but the surface they are walking on is also expanding. Even if an ant walks toward a particular spot on the balloon, the expansion of the balloon surface might carry that spot away faster than the ant can approach. The ant is still moving, but the destination is receding. Light in an expanding universe works similarly. The light is travelling toward us, but the space it travels through is stretching. This expansion is not like an explosion where matter flies outward through pre-existing space. It is space itself that is expanding. Every point in space is moving away from every other point, not because things are flying through space, but because the space between them is growing. Imagine a grid marked on a rubber sheet. As you stretch the rubber, the grid squares get larger. Points that were close together move apart, not because they're sliding across the rubber, but because the rubber itself is stretching. This expansion was discovered by Edwin Hubble in 1929, though the theoretical framework had been developed earlier by Alexander Friedmann and Georges Lemaitre. Hubble observed that distant galaxies appeared to be moving away from us, and the farther away they were, the faster they receded. This relationship, now called Hubble's law, showed that the universe was expanding uniformly in all directions. The expansion rate is described by the Hubble constant, currently measured at about 70 km per second per megaparsec. A megaparsec is about 3.3 million light-years. This means that for every 3.3 million light-years of distance, the recession velocity increases by 70 km per second. A galaxy 10 megaparsecs away is receding at 700 km per second. A galaxy 100 megaparsecs away is receding at 7,000 km per second. A galaxy far enough away is receding faster than the speed of light, not because it is moving through space faster than light, but because the space between us is expanding so rapidly. And yes, you read that correctly. Some galaxies are receding from us faster than the speed of light. This does not violate relativity because they are not moving through space faster than light. The space itself is expanding. Imagine dots on that balloon again. As you inflate it, dots far apart move away from each other faster than dots close together, even though none of the dots are moving across the surface. The recession is due to the expansion of the surface itself. The most distant objects we can observe are so far away that their light has been stretched by the expansion of space into longer, redder wavelengths. The farther away something is, the more its light has been redshifted. The most distant objects are redshifted so much that their visible light has been stretched into infrared wavelengths. Invisible to our eyes, but detectable by infrared telescopes. 93 billion light-years across. Let us try to make this slightly less abstract, even though it will still be utterly impossible to truly comprehend. If you could travel at the speed of light, you would need 93 billion years to cross from one edge of the observable universe to the other. But the universe is only 13.8 billion years old. Light leaving one edge of the observable universe now, heading toward the opposite edge, will never arrive because the expansion of space is carrying the two edges apart faster than light can bring them together. This creates a cosmic horizon, a boundary beyond which we can never see, no matter how long we wait. Objects beyond this horizon are not invisible because they are too faint or too far away in a simple sense. They're invisible because the expansion of space means their light will never reach us. The space between us and them is expanding faster than light can cross it. The horizon is at about 46.5 billion light years, and beyond it lies a region of the universe that is forever hidden from our view. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains billions or trillions of stars. The total number of stars in the observable universe is estimated at around 10 to the 24th power, 1 followed by 24 zeros. Written out, that is 1 septillion stars. To put that in a different context, there are more stars in the observable universe than grains of sand on all the beaches on Earth. Far more, orders of magnitude more. And yet, despite these incomprehensible numbers, despite the vast scale, the observable universe is mostly empty space. The average density of matter in the universe is less than 1 atom per cubic meter. That is an almost perfect vacuum by any terrestrial standard. The stars, the galaxies, the clusters of galaxies, all of it is just a tiny fraction of the volume. Most of space is empty, with just occasional concentrations of matter forming the structures we see. The edge of the observable universe shows us the universe as it was 13.8 billion years ago, shortly after the Big Bang. We cannot see the Big Bang itself because for the first 380,000 years after the Big Bang, the universe was too hot and dense for light to travel freely. Matter and radiation were coupled together in a hot plasma, and photons could not travel more than a short distance before being absorbed and re-emitted. Only when the universe cooled enough for atoms to form did light finally break free and stream through space. That moment of liberation is what we see when we look at the cosmic microwave background radiation. This is the faint glow of light that fills the entire universe, the stretched and cooled remnant of the hot plasma from the early universe. It shows us the universe at 380,000 years old, the earliest time we can see with light. It is the baby picture of the cosmos, and it shows a nearly uniform glow with tiny temperature variations of only a few millionths of a degree. Those tiny variations were the seeds of all structure, the slight density differences that would eventually grow into galaxies and clusters and the vast cosmic web we see today. Beyond the observable universe, there is presumably more universe. The universe might be infinite in extent, or it might curve back on itself in some higher dimensional topology we cannot easily visualize. We do not know. What lies beyond our cosmic horizon is unknowable with light-based observations, because the light from those regions has not had time to reach us and never will. The universe might be vastly larger than what we can see. It might be infinite. We are limited to observing our local bubble, 93 billion light-years wide, expanding slowly as the universe ages and light from slightly farther away has time to reach us. The expansion of the universe is accelerating, driven by something called dark energy. Dark energy is a mysterious component that makes up about 68% of the universe's total energy density. We do not know what it is. We only know that it causes the expansion to accelerate over time. This acceleration means that galaxies currently at the edge of our observable horizon will eventually recede beyond it, disappearing from view as the space between us expands faster than their light can reach us. In the far future, trillions of years from now, if the acceleration continues, most of the galaxies we can see today will have receded beyond our cosmic horizon. Future civilizations, if they exist, will live in a much lonelier cosmos, able to see only their local cluster of galaxies, with everything else having disappeared beyond the horizon. The cosmic microwave background will have cooled and redshifted into invisibility. The evidence for the Big Bang, for cosmic expansion, for the larger universe, will have faded away. This is one of the strange consequences of living in an expanding universe with accelerating expansion. The amount we can see is not fixed. It changes over time. Right now we live in a special epoch where we can see evidence of the Big Bang, can observe distant galaxies, can trace the history of the cosmos. In the deep past, the universe was smaller and hotter, and observers would have seen a very different sky. In the far future, the universe will have expanded so much that future observers will see almost nothing beyond their local galactic neighborhood. This is the ultimate scale. There is nothing larger we can measure or observe. The observable universe is as big as big gets in any meaningful sense. And here is the truly staggering thing. This scale, this 93 billion light-year expanse, is measured in light years. The unit we started with, the distance light travels in 1 year, scales up to measure the entire observable cosmos. Think about that journey. From a light second, the distance to the moon, to light minutes, the distance to the sun, to light years, the distance to stars, to millions of light years, the distance to nearby galaxies, to billions of light years, the distance across the observable universe. The same unit scaled up by factors of billions, measuring everything from our nearest neighbour to the edge of all we can see. And in all that vastness, in all those billions of light years, the one thing that remains constant is the speed of light itself. Light always travels at the same speed in a vacuum, always covers the same distance in a year, no matter where or when that light is travelling. That constancy is what makes the light year work as a unit. It is an unchanging standard in a dynamic universe. There is a profound consequence of working with light years that we have touched on but not fully explored. When you look into space, you are looking back in time, not metaphorically, literally. Every observation of anything beyond Earth is an observation of the past. This transforms astronomy into a form of archaeology, a way of excavating history not by digging into the ground but by peering into the sky. Look at the sun, and you see it as it was 8 minutes ago. Look at Proxima Centauri, and you see it as it was 4 years ago. Look at a star 100 light years away, and you see it as it was when your great-grandparents were young. Look at Andromeda, and you see it from 2.5 million years ago, when early human ancestors were just learning to use stone tools. Look at a galaxy 10 billion light years away, and you see it from when the universe was less than 4 billion years old, long before Earth even existed. This means that the farther out we look, the further back we see. Astronomers use the term look-back time to describe this. The look-back time to an object is how far back in the past we are seeing it. For the cosmic microwave background, the look-back time is about 13.8 billion years, almost the entire age of the universe. We are seeing the universe as it was just 380,000 years after the Big Bang. This is not a limitation. This is an incredible gift. It means we can study the history of the universe directly by looking at different distances. Want to see what galaxies looked like 10 billion years ago? Look at galaxies 10 billion light years away. Want to understand star formation in the early universe? Observe galaxies at high redshift, far away and therefore far back in time. The cosmos presents its history to us if we know how to look. Every deep field image taken by telescopes like Hubble or the James Webb Space Telescope is a time machine. These images show galaxies at various distances, which means at various points in cosmic history. Some galaxies in these images are relatively nearby, showing the universe as it was maybe a few 100 million years ago. Others are so distant that we see them from when the universe was less than 1 billion years old, a time when the first generation of stars was still forming. Galaxies evolve over time. Early galaxies were smaller, more chaotic, filled with young hot stars and intense star formation. Over billions of years they grew through mergers, formed stable spiral or elliptical structures, developed supermassive black holes at their centers, and aged as their populations of stars grew old and red. By comparing galaxies at different distances, and therefore different cosmic epochs, astronomers can trace this evolution, can watch galaxies grow and change across billions of years of cosmic history. Consider what this means practically. When astronomers want to understand how galaxies like the Milky Way formed, they cannot watch a single galaxy evolve. Galaxies take billions of years to change significantly, far longer than human lifetimes, or even than human civilization has existed. But they can observe many different galaxies at many different distances, seeing snapshots from different points in cosmic time. A galaxy 2 billion light years away shows them what galaxies looked like 2 billion years ago. A galaxy 8 billion light years away shows them what galaxies looked like 8 billion years ago. By assembling these snapshots, they can reconstruct the story of galactic evolution. It is like finding a series of photographs of a tree at different ages. You cannot watch a single tree grow from sapling to full maturity. That takes too long. But if you have photographs of many different trees at many different ages, you can piece together the process of how trees grow. That is essentially what astronomers do with galaxies, using distance as a proxy for time. There is something haunting about this. When we observe a galaxy 10 billion light years away, we are seeing light that has been travelling toward us for 10 billion years. That galaxy, as it is today, is invisible to us. We will not see its current state for another 10 billion years. If that galaxy experienced a supernova explosion today, we would not know until 10 billion years from now. And if intelligent beings in that galaxy are looking back at us, they're seeing our solar system as it was 10 billion years ago, before Earth existed, when the Sun was still a young star with a protoplanetary disk. This creates strange paradoxes when you try to think about simultaneity across cosmic distances. What does it mean for two events to happen at the same time, if they are separated by billions of light years? From our perspective, we can only see one of those events billions of years after it happened. From the perspective of someone at the location of that event, our now is billions of years in their future. There is no universal clock, no cosmic now that applies everywhere. Einstein taught us that simultaneity is relative, that observers moving at different speeds will disagree about whether two distant events happened at the same time. But even without considering the effects of motion and relativity, the finite speed of light creates this temporal disconnection. The universe has no universal now. Events that are simultaneous for one observer are not simultaneous for another observer at a different location, simply because light takes time to travel between them. The universe has no universal now. Events that are simultaneous for one observer are not simultaneous for another observer moving at a different speed, a consequence of special relativity. But even without considering relativity, the finite speed of light means that now is a local concept. We can only experience now here at Earth. Everywhere else we see then, and the farther away we look, the older that then becomes. This has profound implications for how we think about the universe. When we look at a deep field image showing 10,000 galaxies, we are not seeing a snapshot of the universe at one moment. We are seeing a timeline, a collection of moments from across billions of years of cosmic history, all visible simultaneously because the light from different galaxies left at different times and arrived at the same moment. It also means that any comprehensive view of the universe must account for this time delay. Maps of the universe show galaxies at their observed positions, but those positions are where the galaxies were when the light left them, not where they are now. A galaxy 1 billion light years away has had 1 billion years to move since its light began travelling toward us. In that time, it has continued orbiting, moving through space, possibly merging with other galaxies, evolving. The map shows the past, not the present. Astronomers have developed techniques to account for this. When they model the distribution of galaxies or the structure of the cosmic web, they can extrapolate forward, estimating where galaxies should be now based on their observed motions and the expansion of space. But these are models, extrapolations. The actual current state of distant galaxies is fundamentally unobservable. We will not see it until the light from now has time to reach us. This is the nature of cosmic distances. They're inherently temporal. 1 light year is not just a distance. It is 1 year of travel time for light, which means 1 year of lag between event and observation. The farther away something is, the older the information we receive from it. Distance and time are intertwined in a way that our everyday experience does not prepare us for, but which is fundamental to how the universe works. For astronomers, this is both a challenge and an opportunity. It is a challenge because studying the universe as it is now across vast distances is impossible. It is an opportunity because we can study cosmic history directly, can observe the universe at different ages, can trace how structures form and evolve. We are historians and archaeologists, digging not into soil but into space-time, excavating the past by measuring light from distant sources. Think about the cosmic microwave background radiation, that faint glow of ancient light from the early universe. When we observe it, we are seeing photons that have been travelling for 13.8 billion years. These photons were released when the universe was just 380,000 years old when it finally became transparent to light. They have been streaming through space ever since, gradually losing energy as the expansion of space stretched their wavelengths from visible light to microwaves. Those photons have crossed almost the entire observable universe to reach us. They have witnessed, in a sense, the entire history of cosmic evolution. They left when there were no galaxies, no stars, just a hot, dense plasma beginning to cool. They travelled through the dark ages of the universe, before the first stars formed. They watched as the first galaxies coalesced, as stars ignited, as heavy elements were forged in stellar cores and scattered by supernovae. They saw the cosmic web form, galaxies clustering into groups and clusters and superclusters, and then, 13.8 billion years after beginning their journey, they arrived at Earth, where we captured them with telescopes and learned from them the story of the universe's infancy. Every photon is a time capsule, every observation is archaeology, and for anyone trying to comprehend the scale of the universe, this temporal aspect adds another layer of incomprehensibility. Not only are the distances impossibly large, but they represent journeys through time as much as through space. Every light year is a year of history, a year of cosmic evolution, a year of change. 46 billion light years to the edge of the observable universe means 46 billion years of history compressed into the radius of our observable sphere, a timeline stretching from almost the beginning of time to now, all visible if you know where to look and have the right tools to see. The universe is a living museum of its own past. We do not need to imagine what the early universe looked like. We can observe it directly by looking far enough away. We do not need to speculate about how galaxies formed. We can watch them forming in distant regions of space, seeing them as they were billions of years ago. This is one of the great gifts of cosmology, this ability to witness history, to see the past by looking into the distance. And it all stems from one simple fact. Light travels at a finite speed, and space is big. Those two truths combine to create a universe where distance and time are the same thing, where every observation is a glimpse into history, where the farther you look, the further back you see. The light year encapsulates this truth, measures it, makes it concrete. 1 light year of distance equals 1 year of look-back time. It is distance and history in a single unit, space and time intertwined. We have thrown numbers around for thousands of words now, trillions of kilometers, billions of light years, septillions of stars. These numbers are precise, they're correct, and they're utterly useless for developing any kind of intuitive understanding. So let us try a different approach. Let us scale things down, make comparisons, use metaphors, and see if we can find any way to make cosmic distances feel even slightly less abstract. Imagine you could travel at the speed of light. This is impossible according to physics. Anything with mass cannot reach light speed, but let us pretend. You are now moving at 300,000 kilometers per second. At this speed, you could circle the Earth more than 7 times in a single second. The Moon, 1 second away. Mars at its closest approach? About 3 minutes. Pluto, 5.5 hours. The edge of the solar system? A year or 2. Proxima Centauri, 4.25 years. Now imagine you are travelling at light speed and you decide to cross the Milky Way. You pick a spot on one edge of the galaxy and aim for the opposite edge, 100,000 light years away. You maintain light speed, never slowing, never stopping. 100,000 years later, you arrive. In that time, human civilization rose from hunter-gatherers to agricultural societies, to industrial civilizations, to spacefaring species and probably beyond. You crossed the galaxy once. Now you decide to visit Andromeda. 2.5 million years at light speed. You leave Earth when early hominids are just figuring out stone tools. You arrive as humans are inventing smartphones. The entirety of human evolution, from primitive ancestors to modern civilization, happens during your trip, and you are traveling at the speed of light the entire time. Now you decide to cross the observable universe. 93 billion years at light speed. Except the universe is only 13.8 billion years old. You cannot make this trip. Even light leaving from one edge of the observable universe at the Big Bang would not reach the other edge. The expansion of space makes the journey impossible even for light. Let us try a different comparison. If you scale down the solar system so the distance from Earth to the Sun was 1 meter, the solar system would still be enormous. Neptune would be about 30 meters away. The Oort cloud would be roughly 15,000 meters away, 15 kilometers, and Proxima Centauri would be 270,000 meters away, 270 kilometers. That is the distance from London to Paris, roughly. On this scale, the Milky Way would be about 6 billion kilometers across. Or try this. If you made a scale model where the Sun was the size of a basketball, Earth would be the size of a peppercorn about 26 meters away. Jupiter would be a ping-pong ball 139 meters away. Neptune would be a grape about 450 meters away. And Proxima Centauri would be another basketball 6,900 kilometers away. That is farther than the distance from New York to London. The galaxy would be about 185 million kilometers across at this scale. Roughly the actual distance from Earth to the Sun. Here is another way to think about it. Light is fast, absurdly fast. In 1 second, light can travel far enough to circle the Earth more than 7 times. That is mind-bogglingly quick by any terrestrial standard. A spacecraft moving at that speed could travel from New York to Los Angeles in about 16 milliseconds. You could go around the world while someone is in the middle of snapping their fingers. And yet, despite this incredible speed, light takes 4¼ years to reach us from Proxima Centauri. The fastest thing in the universe, moving without pause, needs more than 4 years to cross that gap. What if we tried to drive there? At highway speed, 60 miles per hour, never stopping, never slowing, it would take about 44 million years. That is 10 times longer than modern humans have existed. That is longer than the entire history of the genus Homo. You would need to maintain that speed through ice ages and mass extinctions, through the rise and fall of countless species, through continental drift and mountain building and erosion. And you would still not even be halfway there. What if you walked? At 3 miles per hour, a comfortable walking pace, Proxima Centauri is 950 million years away. Let me put that in perspective. 950 million years ago, life on Earth was exclusively single-celled. There were no plants, no animals, no fungi, nothing but bacteria and archaea floating in the oceans. The first multicellular life would not appear for another 300 million years. The first land plants were 600 million years in the future. Dinosaurs were 750 million years away. Humans? 949.5 million years in the future, give or take. If you started walking toward Proxima Centauri 950 million years ago, walking continuously at 3 miles per hour, you would be arriving right about now. And in all that time, life would have evolved from single cells to the staggering diversity of complex organisms we see today. Continents would have assembled and broken apart multiple times. The face of the Earth would have been utterly transformed, and you would have been walking 1 foot in front of the other, crossing the cosmic void. These comparisons help a little, maybe. They give you something tangible to compare to, some way to anchor the numbers to things you can visualize, but they still fail ultimately, because the scales are too different. No matter how you shrink the universe, no matter what comparisons you make, the gulf between human scales and cosmic scales remains vast. Let us try yet another approach. Think about the emptiness of space. If you took all the matter in the universe and spread it out evenly, the average density would be about 1 hydrogen atom per cubic meter. 1 atom in a volume the size of a large closet. That is the average. In reality, matter clusters, so some regions are far denser and others are far emptier, but the average gives you a sense of how much nothing there is relative to something. The space between stars is even emptier than that. In interstellar space, the density is more like 1 atom per 10 cubic centimeters. That sounds denser, but remember that these atoms are spread across light years. Between the Sun and Proxima Centauri, across that 40 trillion kilometer gap, there might be a few billion atoms of hydrogen. That sounds like a lot until you realize that a single breath you take contains more than 10 billion atoms. The entire void between us and our nearest star contains less matter than what you breathe in with every inhalation. This emptiness is hard to appreciate. When we think of space, we often think of stars and planets and nebulae, the stuff we see in pictures. But space is mostly not those things. It is the gaps between them, and those gaps are so much larger than the things themselves that the things become almost irrelevant. If you removed all the matter from the universe and kept the emptiness, you would barely notice the difference. Here is one more comparison that might help, or might make things worse. The nearest galaxy to the Milky Way, excluding small satellite galaxies, is Andromeda at 2.5 million light-years. Now, both the Milky Way and Andromeda are about 100,000 light-years across, so the distance between them is about 25 times their diameter. That might not sound too bad. Imagine 2 coins placed about 25 coin diameters apart. You can visualize that, but now scale it up. Those coins are 100,000 light-years across. The gap between them is 2.5 million light-years. That gap would take light 2.5 million years to cross. If a civilization in Andromeda sent us a message today, traveling at the speed of light, we would receive it 2.5 million years from now. If we sent a reply immediately, they would get it 5 million years after they sent the original message. A simple exchange of hellos would take 5 million years, and Andromeda is close. It is our nearest large neighbour. Most galaxies are far more distant. The typical distance between galaxies and clusters is millions of light years. The typical distance between galaxy clusters is tens of millions of light years. The observable universe extends for tens of billions of light years, containing hundreds of billions of galaxies, each separated from its neighbours by millions of light years of emptiness. Perhaps the most honest comparison is this. The universe is big in a way that breaks human comprehension. Not big as in a really big building or a really big country. Big as in so large that the human brain, evolved to understand distances of meters and kilometers, simply cannot process it. We can measure it. We can calculate with it. We can use it to make predictions and test theories. But we cannot feel it, cannot internalize it, cannot make it fit into the way our brains naturally understand space. And maybe that is important to accept. Maybe we should stop trying to make cosmic distances intuitive and just accept that they are not, and never will be. They exist on a scale our minds cannot reach, and that is okay. We have tools, mathematical and technological, that let us work with these scales anyway. We do not need intuition to measure and map the universe. We need instruments and equations and observations. But there is still something valuable in making the attempt, in trying to find comparisons and metaphors, even if they ultimately fail, because the process of trying forces us to confront how vast the cosmos truly is. It forces us to reckon with our smallness, not in a nihilistic way, but in a way that inspires awe. We are tiny, we are insignificant in terms of scale, and yet we have figured out how to measure the immeasurable. We have mapped the universe from our small blue planet. We have looked out into the void and understood what we saw. Consider this. Every photon that enters your eye from a distant star has been on a journey. It left that star years or centuries or millennia ago. It crossed the vast emptiness of space, threading through the galaxy, avoiding collisions with dust and gas, surviving the journey to arrive precisely at your retina. And there are billions of these photons entering your eyes every second when you look at the night sky. Each one is a messenger from the past, a tiny packet of information that has crossed incomprehensible distances to deliver its message. You are, in a very real sense, connected to those distant stars by these photons. The light that left Proxima Centauri 4¼ years ago connects you to that star across 4¼ light years of space. You're seeing it not as it is, but as it was, but you're still seeing it. The information reaches you. The connection exists even if it is delayed by years. This is true for everything in the night sky. Every star you can see is connected to you by photons that have crossed the void. Some of those photons left their stars when you were a child. Some left when your grandparents were young. Some left before modern civilization existed, and yet they all arrived tonight, all visible in the same moment, connecting you to a web of stars across space and time. That is remarkable. That might be the most remarkable thing our species has ever done. We are limited creatures in a limitless cosmos, and we have transcended those limitations not by becoming infinite ourselves, but by building tools and methods that let us measure infinity anyway. The lightyear is one of those tools. It is a bridge between our limitations and the universe's vastness. There is something profoundly human about what we have been discussing. We are creatures who evolved to navigate forests and grasslands, to throw spears at prey, to recognize faces across a campfire. Our brains developed to handle distances of meters and kilometers, times of seconds and days, quantities of ones and tens. Nothing in our evolutionary history prepared us to think about light years or billions of years or septillions of stars. And yet, here we are. We have measured the distance to the nearest stars. We have mapped our galaxy. We have calculated the size of the observable universe. We have done something that should be impossible. We have comprehended, at least mathematically, things that our intuition cannot grasp. This is worth pausing to appreciate. Consider the audacity of it. Ancient humans looked up at the stars and saw lights in the sky. They did not know what stars were. They thought they might be holes in the celestial sphere through which divine light shone, or tiny fires suspended somehow in the air, or the souls of the dead. They created myths and stories to explain what they saw, because that is what humans do when faced with mysteries. But somewhere along the way, someone had a different idea. What if we could measure the distance to those lights? What if we could figure out what they are, how far away they are, how they work? This was an absurd ambition. The stars seemed unreachable, unknowable, beyond human understanding. But humans tried anyway. The first attempts failed. Ancient Greeks like Aristarchus tried to measure the distances to the sun and moon using geometric methods. They got the basic ideas right, but their measurements were wildly inaccurate because the angles involved were too small for their instruments. For 2,000 years, astronomers tried to measure the parallax of stars, the tiny shift in their apparent position as Earth orbits the Sun. For 2,000 years they failed, but they kept trying. They built better instruments, they made more careful observations, they developed more precise mathematical methods, and finally, in 1838 Friedrich Bessel succeeded. He measured the parallax of 61 Cygni, calculated its distance, and proved that the stars were vastly farther away than anyone had imagined. He opened the door to measuring the universe. Since then, the pace of discovery has been breathtaking. Within a century of Bessel's measurement, astronomers had discovered that our galaxy was just one of billions, that the universe was expanding, that space and time were intertwined in ways Einstein described. Within another century, we had mapped the cosmic microwave background, detected gravitational waves, photographed black holes, discovered thousands of planets orbiting other stars. We have gone from not knowing the distance to the nearest star to mapping the structure of the observable universe in less than 200 years. That is an eye blink in human history. It is less than 1/1,000,000th of the age of the universe. And yet, in that brief span, we have learned things about the cosmos that seemed forever beyond our reach. This is possible because humans have a unique ability. We can build tools that extend our senses. We cannot see distant galaxies with our naked eyes, so we build telescopes. We cannot measure tiny angles, so we build precise instruments. We cannot intuitively grasp huge numbers, so we invent mathematics. We cannot travel to distant stars, but we can send light and radio waves and analyze what comes back. Every measurement of cosmic distance is a triumph of human ingenuity. When we say Proxima Centauri is 4.24 light-years away, that number represents centuries of accumulated knowledge. It represents the invention of calculus and trigonometry. It represents the development of precision instruments that can measure angles to millionths of a degree. It represents an understanding of how stars work, how light travels, how space and time relate to each other. The light year itself is a testament to human cleverness. We needed a unit of measurement that could handle cosmic scales, and we invented one. We could have given up, could have said the stars are very far away and left it at that, but we did not. We created tools and units and methods that let us measure even what we cannot comprehend, and we are not done. New instruments are constantly pushing the boundaries of what we can observe. The James Webb Space Telescope, launched in 2021, can see galaxies more than 13 billion light-years away, showing us the universe when it was only a few 100 million years old. Ground-based telescopes with adaptive optics can correct for atmospheric distortion and achieve resolutions approaching theoretical limits. Radio telescope arrays can combine signals from instruments across the globe to create virtual telescopes the size of Earth. Future missions will do even more. Plans exist for space telescopes that could directly image planets around nearby stars, perhaps even detect signs of life on those worlds. Gravitational wave detectors will become more sensitive, letting us observe colliding black holes and neutron stars billions of light-years away. New techniques might let us probe the universe even earlier than the cosmic microwave background, seeing echoes of the first fraction of a second after the Big Bang. All of this springs from one fundamental human characteristic: curiosity. We want to know, we want to understand, we want to measure and map and comprehend even when comprehension seems impossible. This drive has taken us from wondering what the lights in the sky are to measuring the age and size and contents of the universe. The light year is more than just a unit. It is a symbol of human ambition and human achievement. It says that even though we are small, even though we are limited, even though we live for only a few decades on a small planet orbiting an ordinary star, we can still reach out across the cosmos with our instruments and our mathematics and our minds. We can measure the unmeasurable. We can know the unknowable, at least in part. Think about what it means that you, sitting wherever you are right now, can know how far away Andromeda is. 2.5 million light-years. That knowledge exists because humans decided the stars were not beyond understanding, were were not forever mysterious. Someone decided to try to measure them, and someone else improved on that measurement, and someone else built on that work, and on, a chain of human efforts spanning centuries, all driven by the simple desire to know. You are the beneficiary of that accumulated knowledge. When you look at the night sky and know you are seeing light that travelled for years or centuries or millions of years to reach you, you're participating in one of humanity's greatest achievements. You're connected across time to every human who looked up and wondered, to every astronomer who tried to measure the distances, to every scientist who built on previous work to understand the cosmos better. This knowledge is not just abstract. It is not just numbers and equations. It is a story about who we are as a species. We are the creatures who look up and ask, how far? We are the ones who, faced with the incomprehensible vastness of space, decide to measure it anyway. We are the ones who build tools and methods and theories to extend our reach far beyond what our unaided senses can perceive. The universe is vast. The distances involved are impossible to truly comprehend. We have said this repeatedly, and it bears repeating because it is important to remember our limitations. But it is equally important to remember that limitations can be worked around, can be transcended through cleverness and effort and the accumulated work of generations. We cannot feel what a light year means. We cannot hold it in our minds the way we hold familiar distances, but we can measure it. We can use it. We can learn from it. And that is enough. That is in fact extraordinary. The light year is not the only unit astronomers use for cosmic distances, though it is perhaps the most accessible to non-specialists. As we have mentioned, professional astronomers often prefer the parsec, which is based on how we measure stellar parallax. 1 parsec equals 3.26 light years, or about 30.9 trillion kilometers. The advantage of the parsec is that it directly relates to the measurement technique. A star with a parallax of 1 arcsecond is exactly 1 parsec away. The math is cleaner for astronomers working with parallax data. For even larger distances, astronomers use kiloparsecs, thousands of parsecs, megaparsecs, millions of parsecs, and gigaparsecs, billions of parsecs. The distance to Andromeda is about 770 kiloparsecs. The observable universe extends for about 14 gigaparsecs. These units scale nicely as distances grow, keeping the numbers manageable. But regardless of the specific unit, the fundamental challenge remains. Measuring distances in space is hard. For nearby stars, we can use parallax, watching how their position appears to shift as Earth orbits the Sun and using trigonometry to calculate their distance. For more distant objects, we need other methods. One key technique uses what are called standard candles, objects with a known intrinsic brightness. If you know how bright something actually is and you measure how bright it appears from Earth, you can calculate how far away it must be. Cepheid variable stars, which pulse regularly with a period related to their intrinsic brightness, are excellent standard candles for measuring distances to nearby galaxies. Type Ia supernovae, incredibly bright explosions with fairly consistent peak luminosity, serve as standard candles for even greater distances. For the most distant objects, astronomers use the redshift of light. The expansion of space stretches light, shifting it toward redder wavelengths. The amount of redshift tells us how much the universe has expanded since the light left its source, which tells us the distance to that source. This technique works for objects billions of light years away, at distances where no other method is practical. New telescopes continue to push the boundaries of how far we can see. The James Webb Space Telescope, launched in 2021, can observe some of the most distant galaxies ever seen, galaxies more than 13 billion light years away, showing us the universe when it was less than 700 million years old. Future telescopes, both ground-based and space-based, will push even farther, observing earlier and earlier epochs of cosmic history. But there is a fundamental limit. We can never see beyond the cosmic horizon, the edge of the observable universe. Light from regions more than 46 billion light-years away will never reach us because the expansion of space is carrying those regions away faster than light can close the gap. As the universe ages, this horizon grows slightly, as light from slightly more distant objects has time to reach us. But it grows slowly, and regions far beyond the current horizon will remain forever invisible. This is not a technological limitation. It is a fundamental feature of the universe. There is a limit to what we can observe, set by the age of the universe and the expansion of space. No telescope, no matter how powerful, can see beyond this boundary. The universe beyond our horizon is not hidden because it's too faint or too far away in a simple sense. It is hidden because the structure of space-time itself prevents light from reaching us. Within that observable sphere, however, we can see a tremendous amount. We can map the distribution of galaxies, trace the cosmic web, measure the rate of expansion, study star formation across cosmic time, detect planets around other stars, and observe phenomena that do not even exist in our region of space anymore, but which we can see because their light is still travelling toward us from the distant past. The future of cosmic distance measurement will likely involve even more sophisticated techniques, better calibrations of standard candles, more precise measurements of the universe's expansion rate, and perhaps new physics that helps us understand dark energy and dark matter, the mysterious components that make up most of the universe's mass energy, but which we can only detect through their gravitational effects. But no matter how the technology evolves, no matter what new techniques we develop, the lightyear will remain a fundamental and useful unit. It connects distance to time in a way that is both mathematically precise and conceptually meaningful. It reminds us that we are always looking into the past, that distance and time are intertwined, that the universe is both a place and a history. And as we continue to explore, as we build bigger telescopes and develop better instruments, as we push the boundaries of what we can observe, we will continue to measure those distances in light years, or in parsecs, or in some other unit that captures the scale of cosmic separations. The numbers will remain incomprehensible, the distances will remain impossible to truly grasp, and we will continue measuring them anyway, because understanding our place in the universe requires knowing how far we are from everything else. We began this journey with a simple question: what is a light year? The answer, we now know, is both simple and profound. It is the distance light travels in 1 year, about 9.5 trillion kilometers, a unit of measurement designed to make cosmic distances slightly less unwieldy. But it is also much more than that. A light year is a time machine, a way of looking back into history by looking out into space. It is a bridge between the human and the cosmic, between our limited understanding and the limitless expanse of the universe. It is a reminder that we are small, that we exist on a tiny planet orbiting an ordinary star in the suburbs of an average galaxy in a universe containing hundreds of billions of galaxies spread across billions of light years. And yet, despite our smallness, despite our limitations, we have measured all of this. We have mapped the cosmos. We have traced the evolution of galaxies across billions of years. We have looked back to near the beginning of time. We have done something that should be impossible. We have comprehended, at least intellectually, things we cannot possibly comprehend intuitively. Your brain still cannot really grasp what 1 trillion kilometers means. Mine cannot either. No human brain can. We are not built for that. But we can work with these numbers, calculate with them, learn from them. We can use light years and parsecs and redshifts to measure the universe, to understand its structure, to predict its future. We can transcend our limitations not by overcoming them, but by building tools and methods that work despite them. The universe is vast beyond imagining. The distances between things make the things themselves seem almost irrelevant. Space is mostly empty, mostly void, with matter being the rare exception rather than the rule. And yet within that vastness, within that emptiness, connections exist. Light travels from one star to another, carrying information, making observation possible. Gravity reaches across the void, shaping the motions of galaxies separated by millions of light years. We are connected to the rest of the universe not by proximity but by physics. The same laws that govern motion on Earth govern motion in distant galaxies. The same particles that make up our bodies make up stars across the cosmos. The atoms in your body were forged in stars that exploded billions of years ago, scattering their contents across light years of space, eventually collecting into clouds that formed new stars and planets, including Earth and you. In a very real sense, you are made of starlight and stardust and time. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in the cores of stars or in the explosions that ended their lives. You are the universe examining itself, a collection of particles organized in such a way as to be capable of wondering about cosmic distances, and those distances, those incomprehensible light years, a part of what makes existence so strange and beautiful and terrifying. We exist in a universe so large we cannot comprehend it, separated from our nearest neighbours by gaps we can never cross, able to observe but never interact with most of the cosmos. And yet here we are, tiny creatures on a small world, looking up at the night sky and understanding, at least in part, what we see. If you found this journey through cosmic distances fascinating or your mind hurts in the best possible way, hit that like button. Subscribe for more explorations of topics that make reality seem stranger than fiction, because the universe is strange. It is vast and old and filled with mysteries we're only beginning to understand, and measuring it, mapping it, learning its secrets, that is one of the great adventures of human existence. Thank you for joining me on this trip from the moon to the edge of everything we can see. The next time you look up at the stars, remember that you are looking back in time, that every photon hitting your eye has been travelling for years or centuries or millennia. Remember that the distances involved are so large they break comprehension, but we measure them anyway. And remember that in a universe measured in light years, on a planet orbiting an ordinary star, you're here, now, capable of understanding all of this. And that might be the most remarkable thing of all.